In this video, I'm going to introduce you to the supermagic formula, which can be used to calculate the acceleration of a point in a fixed frame when you're using multiple reference frames. But before I jump right into introducing the supermagic formula, I just want to review the following. If we have a point P and we want to express its kinematics in some frame A, as shown here, so frame A with the unit vectors A1 and A2, and we have this position vector ROP. And we just write out if ROP is our position vector, we can get the velocity of point P in frame A by taking the time derivative of the position vector in frame A. Now, of course, sometimes that's we express ROP not in terms of the unit vectors of frame A, but in the unit vectors of frame B. For instance, you could write ROP, you could use the fact that this vector has a length of L and is rotated with respect to A1 by theta, and you could write out L cosine theta A1 plus L sine theta A2, or as we introduced last week, you could utilize a second reference frame, so we're going to call this reference frame B, so we have B1 and B2. And if you choose the orientation of that reference frame cleverly, specifically if you orient one of the unit vectors in the direction of the position vector, you can simplify ROP, or you can write it in terms of the unit vectors of frame B, and here it's simply LB1, right? So you hopefully notice that writing the position vector in terms of the unit vectors of frame B is much simpler than if you wrote it in terms of the unit vectors of frame A. Right, and that's the whole point of using multiple reference frames. Right? Again, we chose this orientation of frame B so that B1 points in the same direction as our position vector of interest. So that simply expressing the position vector can be done by multiplying the magnitude of that position vector, which in this case is L, by this unit vector B1. So now that's great, but of course things got a little bit more complicated because we now want to calculate the velocity of that point in frame A, but we have our position vector that's written in terms of the unit vectors of B1. And so to do that, we use the magic formula, which says that the velocity of point P in frame A is equal to the time derivative of our position vector in frame B plus the cross product between the angular velocity of frame B in frame A and the vector itself. And so just quickly, just to write this term out, we can actually write that as the velocity of point P in frame B. Okay, so this is just the general formula for calculating the velocity. But importantly, this is true when frame A and frame B share the same origin. Now, of course, there are other cases when we have a rotated frame and it doesn't share the same origin as our fixed frame. For example, if you remember the power button on the DJ Roomba example. So again, here we have our fixed frame A, A1, A2, frame O. And we introduced a second frame, but we put the origin of that frame at point R. So R, and then again we draw our frame B in this manner, and again that's so that we can express this vector position vector that goes from R to P. We can express that in terms of just one unit vector, which in this case is B1. So just to say that again, we have our position vector ROP. That's our vector of interest. And we get ROP by summing these two vectors here. So that's R, O, R plus R, RP. And as I mentioned, we generally write ROR, or in the past have written ROR in terms of frame A. I'm just going to circle this. This is frame A. Right, so here we would write that as some magnitude in the A1 direction and some magnitude in the A2 direction to get us to this point R here. But then RP, that position vector, we would write that in frame B. So again, just to put some numbers to this, this should be very familiar. If we were writing out ROR and RRP for this specific example here, we would write ROP is equal to some magnitude in the A1 direction plus some magnitude in the A2 direction plus, and we'll call it some magnitude along the B1 direction, we'll just call that L. And so plus L B1. So again, this part here, this is our RP, and this is our OR. You may also remember that when we wanted to calculate the velocity in this example, so the velocity of point P in frame A, of course we take the time derivative in frame A of ROP, and because we were using the magic formula, we divided these terms up, right? So we took the derivative of all of the terms expressed in A1 and A2 unit vectors, put that in one, and then we took the time derivative in frame A of the terms expressed with frame B unit vectors as such. And so to write this more generally, what we did was we took the velocity, so the velocity of point P in frame A is equal to the velocity of point R in frame A, right? So this chunk here plus the velocity of point P in frame B, and then again you have your plus the cross product of the angular velocity of frame B in frame A with our position vector R, RP. So this right here is the general formula for calculating the velocity of a point when you're using multiple reference frames, except for the fact that the origin is of your second frame, frame B, is just not at the same point as the origin of frame A. This should be pretty straightforward, right? The only difference between the two expressions here is this term, right? This velocity of point R in frame A, right? And that just simply falls out from here. But the reason I went through the exercise of defining what the general form or general equation for calculating velocity, especially in this latter case where the origins of frame B and frame A don't line up, is because we're going to use this formula to derive the super magic formula, which allows us to calculate the acceleration now of a point P of interest. And again, we're going to talk about the case where the origins of frame A and frame B are not lined up. Because again, this is just a more general scenario. You can obviously get from this equation here to this equation, right? So our first example was a more restricted version of the following. Hopefully you can see how to get there, right? But if you can't, just let me know. And so with this, let's introduce the super magic formula. The super magic formula is for any position vector written in the form ROP equal to ROR plus RP, where ROR is written in frame A and RP is written in frame B, in which the velocity, as we literally just said, is VAP is equal to V of R in frame A plus the velocity of point P in frame B plus the cross product of the angular velocity of frame B and frame A and our position vector RP, right? So in this case here, we can write out the acceleration, and this is what is the super magic formula. Get ready for the big reveal. Is that the acceleration of point P in frame A is equal to the acceleration of point R in frame A plus the acceleration of point P in frame B plus 2 of the times the angular velocity of frame B and frame A multiplied, or taken with the cross product to the velocity of point P in frame B plus, now I'm introducing this term here, so this alpha, this is the angular acceleration, so I'll define that in just a moment, but we have the angular acceleration of frame B in frame A crossed with our position vector RP plus the angular velocity of frame B in frame A crossed with the angular velocity of frame B in frame A, again crossed with our position vector RP. This here is the super magic formula. Given the length, I'm sure you can tell why it's called super. But this is very, very helpful in terms of calculating the acceleration. So that once you calculate each of these terms individually, you can get at this acceleration quite quickly. And again, for reference, I mentioned that we have this new term alpha, or this new vector alpha, and that is the angular acceleration of frame B with respect to frame A. So that is the time derivative of our angular velocity of frame B in frame A. And so this equation might look long, it might look daunting, but I will show you in the next few videos how it can be helpful. But first, I'm actually going to walk through the steps of deriving this to show you why this equation is in fact true.